All right, so the last section we're going to look at this week is 5.6, and it's going to be reviewing a lot of the things we've already done with vectors, but now 3D instead of 2D. Okay, it's going to be very similar. All right, so first thing to kind of understand in 3D is how the axes work. The x, the y, and the z axis are all perpendicular to each other. And the way you can kind of visualize which axis goes in which direction is using your right hand. What's that?
Backwards to look at.
Oh, yeah, use your right hand, because don't use your left hand, it'll come out backwards. But if you use your right hand, your index finger points in the direction of the positive x-axis. The middle finger would point in the direction of the positive y-axis. And the thumb, that's the positive z-axis. If you use your left hand and you line up x and y, what happens is z comes out backwards, points the wrong way. Okay. So because of that, this is called a right-handed coordinate system. Okay. So that's x, y, and z. So we don't really talk about horizontal and vertical as much. Like we used to say x is horizontal, y is vertical. That's not really the case here. You can think of x, y as, this was like a box, like x, y is like the bottom. This is what we've been doing all week, stuff down here. Z is coming up straight off the bottom. Okay, like if this is the desk, Z is up off the desk. And in 3D, you don't have quadrants anymore, you have what you call octants, because there's 8 sections. Like in 2D, you get 4 sections. On 3D, you get 8. And the way I can kind of describe it is, like, let's imagine the board is like is a plane. Okay? You could go like up, right, and come out of the board. You could go up, you could go right, and you could go behind the board. Okay? There's 2. You could go right, down, in front, right, down, behind. There's 2 more. And then left, up, in front, left, up, behind. Left, down, in front, left, down, behind. So there's 8 regions, and they're called octants in 3D. When we write coordinates in 3D, we're going to need an x value, a y value, and then we need a value for the third axis. So we need a z value. So what I'm going to do for each formula is I'm going to put up the 2D version that we've already learned, and then I'll put the 3D version after. So finding the distance between 2 points in 3D is going to be based off the formula in 2D. That's the distance formula in 2D. Okay, we did that way back. It's really just the Pythagorean theorem. The x1, the y1, the x2, and the y2, that's your coordinate. It's like where you're starting and where you're stopping. Now, to do it in 3D, first of all, you need a 3D coordinate. You could essentially think of every problem that we've done, where we've been finding distance. You could think of the z's as being 0 up until today. These were always 0, so we never wrote them down. Now they're not going to be 0. And the formula to do this in 3D, very similar to the formula in 2D. It starts out the same way. But we have to put one more thing on the end of that formula to extend it to work in 3D. Anybody have a guess what's going to be under the box?
Z2 minus Z1 squared.
Yeah, Z2 minus Z1 squared. And that's pretty much how every formula that we're going to review today works. You just take the 2D version and you put on something right at the end that mimics the pattern of what you already have. And that's how you do it in 3D. So this formula we just wrote down, that is the Pythagorean theorem in 3D. That's what it is. Pythagorean theorem in 3D. It makes a lot more sense if you draw it. You can see it. All right, let's just try to see if we can find the distance between those 2 points. So we have the point -1, 3, 2, and 4, -2, 5. All right, so when you're finding the distance, what's the first thing that you usually want to write down?
D equals whether a giant square root.
Yeah, we want to make sure we put down that giant square root so we don't forget the whole thing is going to be a square root. All right, what's going to be my first thing that I put down in parentheses under the root?
Be your x numbers subtracted from each other. Number 2, number 1.
Okay, so can you tell me what I would write?
So open parentheses 4 minus -1 squared.
Okay, that's the first part. 4 minus -1 squared plus. All right, and what's going to be the next part?
-2 minus 3 squared, parentheses.
-2 minus 3 squared. Okay, and Brady, the last part?
Same me.
Yes.
It was 5 minus 2 squared.
5 minus 2 squared. Okay. All right, and Alex, can you simplify what we get in the first parenthesis?
5 squared.
5 squared, yeah, which is
25.
25. And Alex, the second parenthesis?
5 squared again, so 25.
Well, what squared is it again? Well, what squared is it this time?
-5 squared.
-5 squared, yeah. So 25. And then Isaiah, how about the last part?
9.
9. So 5 minus 2 is 3. Squared, you get 9. So what's the distance between these 2 points?
59 squared.
Square root is 59.
Square root of 59. If they'd like a decimal, you just plug it in on the calculator. Otherwise, just leave it like that. All right. So any question on finding the distance between 2 points in 3D? Okay. So next thing is vectors. So again, before we talk about 2D, before we talk about 3D, I'll just review the 2D. In 2D, when we wrote things as unit vector form, we had 2 special unit vectors, I and j. I pointed in the direction of the positive x-axis, j pointed in the direction of the positive y-axis. And we stacked i's and j's together to build a vector. In 3D, we're going to need one more special unit vector. Does anyone have a guess what we're going to call that one?
K.
K. Yep. So now in 3D, I still points in the direction of the positive x-axis. J points in the direction of the positive y-axis. And K points in the direction of the positive z-axis. So now we can stack together i's, j's, and i's, j's, and k's, and we can build any kind of vector we want. Remember, these are the 3 components of the vector. I'm just not going to call them horizontal and vertical anymore, because that doesn't make as much sense in 3D. So I would call this one the x-axis component, the y-axis component, and the z-axis component. That's how you'll see a vector in 3D. Okay, this definition, this is a review from Monday. Does anybody remember what you call a vector that starts at the origin? It has a special name.
the unit?
No, a unit vector is just a vector with a length of 1.
Point vector.
What kind of vector?
Point vector.
It does begin with a P, but not point. But it does begin with a P. A vector that has its initial point at the origin.
Position vector?
Position vector. Yep. That's exactly the same definition you have, or should have, in your notes from one. Right, so no change in that. I'm just repeating it.
Courage.
Yeah, just saying. All right, so one thing we did a lot of in 2D is we did sketching. Now, in 3D, you can still take the end of one vector, the beginning of another vector, connect them together, and draw from where it starts to where it stops in 3D. You can, it works fine. The problem is 3D sketching is kind of hard. So what we're going to do, we're going to stick with just formulas. Okay. So in 2D, that was the formula to find a position vector. Okay. That's from Monday. I want to extend that to 3D. So in 3D, the only difference is your initial and terminal point are going to have a Z number. So looking at the formula in 2D, does anybody have a guess how we're going to extend it for 3D?
With the singularity versus formula.
Yep. So specifically, what did you have to put here?
Comma z2 minus z1.
Yeah, we're just going to do comma Z2 minus Z1. Yep. So basically, if you know all the 3D formulas, that's all you need to know. Because if you don't have a 3D problem, all you have to do is cover up the Z's and use it the way it is. Okay, so x2 minus x1, y2 minus y1, z2 minus z1. So let's try finding a position vector between two 3D points. So there's your 2 points. Negative 1, 2, 3. And 4, 6, 2. So Raina, what's the first thing I'm going to write down right after the angle bracket to find the x component of my vector?
4 minus negative 1.
Okay, so I'm going to have 4 minus negative 1. Chris, what am I going to write down to find the y component?
6 minus 2.
Yep, so we got the 6 minus 2. And Christian, what am I going to write down to get the z component?
2 minus 3.
2 minus 3. Now, does the order matter there? The order you subtract the x's in.
Yep.
Yeah. When you subtract two numbers, it's not the same if you switch it. So yeah, you have to do the terminal point minus the initial point, not the other way. Okay, so 4 minus negative 1, that's going to give me 5, 4, negative 1. That's my position vector written in what the book calls an algebraic vector. How would I write that with I, J's, and K's if they wanted it that way?
5i, 4j, and negative 1k. Negative k.
Like that?
Yeah.
Something we're missing.
5i plus 4j
Plus. Yep. Yeah, I've seen people mix those two notations together, like they do like 5i, comma 4j, comma negative k. Yeah, you can't do that. You can either use the commas with the brackets and no letters, or you use just the letters and you put addition and subtraction signs between them. But don't mix them. Okay, is there any question on writing it either way? All right, so that's finding a position vector. The next thing we did is we took vectors and we, not visually, but numerically, added, subtracted, scaled, and found the magnitude. So now we're going to do that here. Okay. Adding and subtracting vectors, again, visually, you connect the end of one to the beginning of the other, and draw the diagonal. Numerically, it's like combining like terms. Take your x components, combine them. Take the y components, combine those, and then take your z components, and then combine them. Okay, and when I say combine the components, well, the two operations are either combine them with addition, add the x's, add the y's, add the z's, or if the problem is about subtraction, subtract the x's, subtract the y's, subtract the z's. Next thing we did was this. We put something in front of a vector. Does anybody remember what that does to the vector?
Scales it.
Scales it. That's called a scalar. If you want to scale a vector, you multiply each component by the number you're scaling by. So in 2D, you multiply that number by the x component, multiply it by the y component, and in 3D, we're also going to have to multiply it by the z component. Yep. So scaling a vector is just, you got to distribute that scalar out to one more component instead of just two. Okay. And the next formula we looked at was this one with the double bars around a bold letter. What did the double bars mean?
The magnitude of it.
The magnitude. And in 2D, this was the formula for the magnitude. If you look back in your notes from, I think this was the end of class on Monday. So it was the x component squared plus the y component squared. What do you think is under that box to extend this to
Plus
3D?
Z component squared.
Yeah, the z component. And in this case, we're not using the x2, the y2, and the z2 because you're not finding the magnitude of w. You're finding the magnitude of v in this formula. If we were doing w, then you would have used x2, y2, and z2. All right, so any questions on those really four formulas? Let's try a couple and see what we can do. All right, so here are your two vectors. And the first thing I want to do is add them together. Not visually. I don't want to draw a 3D and then connect the diagonal. I want to do it numerically. Okay, so when I add these vectors together, what's going to be my I component? 5i, yep. And the j component?
Negative j.
So I get a negative j, and the k component?
Plus 3k.
Plus 3k. Okay, that's how you can write your answer in what's called unit vector notation. Don't confuse that with the term unit vector. This is not 1 unit long. It's called unit vector notation because it has i's, j's, and k's in it. What if they wanted it in this notation? How would you do it?
5i, comma, negative j, comma, 3k.
No, we're mixing the notations. We can't.
It's just 5, comma, negative 1, comma, 3.
Right. 5, negative 1, 3. There are no ij's and k's in that format because it's not a unit vector notation. All right, so that's the sum of the two vectors. Let's find the magnitude of v. How would I find the magnitude of v?
Square root
Yep, square root.
of 2 plus 3 minus 2 squared to the second power, all of them to the second power.
Okay, so tell me what's going to be the first one.
2 to the second power,
Okay, so we got 2 squared, that's 4.
now plus 9
3 squared is 9.
plus 4.
And then negative 2 squared is also 4. So the magnitude of v would be the square root of
17.
square root of 13 plus 4, which is 17. Okay, any question on that? Bless you. All right, let's try a scalar. So I want to take w, and I want to triple. Okay, on paper, if you were going to triple w, that means you'd take, 3 of the w's and stack them together. Makes it 3 times as long. I just want to do it with numbers. Okay, so anyone think they can tell me what 3w would be?
It would be 3w equals 9i minus 12j plus 15k.
Yep. And again, that's unit vector notation. How would you write this one in unit vector notation?
That's just magnitude.
That's just a magnitude. That's not a vector at all. So yeah, you can't write that in unit vector notation. It's just a number. The answer to A and the answer to C were vectors. The answer to B, it's just a magnitude, just a number. All right. So now, once we found the magnitude of vectors, that was part of finding the angle between two vectors. So that's what we're going to look at next. What's the other thing that we need to know how to do that the formula for the angle of two vectors uses?
We have to find the
Magnitudes is part of it.
the magnitudes, then we have to multiply together to get the dot.
The dot product. Yep. So now we're going to look at how we find a dot product in 3D, and it's exactly what you would expect it to be. Okay. So if I wanted to find the dot product between those two vectors, let's see if you can just figure out what the formula is. What do you think the first two things I would multiply are?
This one next to it.
You're going to multiply the two x components together. And then what's going to come right after that parenthesis?
We're gonna multiply 2 y components.
Something before that.
Adding.
Adding. And then what comes after that?
Multiply the 2 y components.
Yep. Multiply the two numbers that represent your y component. And if that was 2D, you're done. What do you think I have to put down for 3D?
Plus, and then the z's.
Yep. Plus, and then the z1 times z2. So that's the formula for finding a dot product in 3D. Multiply the x's, plus multiply the y's, plus multiply the z's. Okay. So let's see if we can find the dot product between v and w. All right. First two things I would multiply together are?
The i's.
Yep, so tell me what they are.
2i times 5i, which is 10i. Or just 10.
Which one?
for the like 2, like for the i's, like 2 and times 5.
Yeah, just 2 times 5. When you're doing a dot product, you don't have any letters in the answer. So it's just 2 times 5. We can simplify that in a second. All right, what's the next thing we multiply together?
Plus 3 times 3. 3 times negative 3.
Plus
Negative 3 plus 3. Negative 3 times 3.
negative 3 times 3. Yep, negative 3 times 3. And now that's part of it. We need one more part.
6 times negative 1.
6 times negative 1. So do that out, and that's your dot product. So 10 minus 9 minus 6. So the dot product is negative 5. Okay. Any question on how we got the dot product? All right, so now we know how to find a dot product in 3D. We know how to find a magnitude in 3D. So that now allows us to find the what in 3D?
The angle.
Find the angle. Yep. So the angle between 2 vectors in 3D, it's exactly the same formula as 2D. It's just when you do the formula, you're going to be doing a 3-dimensional dot product, which I just showed you how to do right there. You're going to be doing a 3-dimensional magnitude, which we just did over there, and another 3-dimensional magnitude, which we just did over there. So the individual calculations in the formula each have an extra step because they're 3D, but the formula itself is the same formula. So because we already have the dot product, I'm going to copy down the 2 vectors we just had from up above. So 2, negative 3, 6. 2, negative 3, 6. And 5, 3, negative 1. 5, 3, negative 1. All right, so the first thing we need in this formula is already done for us, the dot product. What did we just get when we did the dot product of these 2 vectors?
Negative 5.
Negative 5. So there's the first part. Okay, next thing we need is the magnitude of u. Right. What's going to go under my root?
Anything in a euro?
What's that?
Anything in a euro? Like u equals 2.
So like what's the calculation I have to do under here?
2 squared.
2
plus-
squared
Plus negative 3 squared.
plus negative 3 squared
Plus 6 squared.
plus 6 squared. Okay, and what does that come out to? The square root of
49.
Yep, 4 plus 9 plus 36. That's 49. Which has to come out to a nice answer. Okay, so we got the magnitude of u. We got the dot product. The only other thing we need is the magnitude of v. All right, let's find that. Okay, what's going to go under the square root to get the magnitude of v?
5 squared
Okay, so 25
plus 9 or 3 squared.
squared, which is 9.
And then minus 1 or plus 1 because it's squared.
Yeah, so plus, and then negative 1 squared would be 1. Okay, and what's that come out to?
Square root of 33.
35.
35. Right. So it doesn't come out to a nice answer, but that's okay. All right, so now remember the question is find the angle. Okay, so what goes on the left side in the formula to find the angle? Cosine theta. What goes in the top on the right side?
-5.
-5. Okay. And what goes in the bottom?
Square root of 35 times 7.
Square root of, yeah, I'm just going to put the 7,
Because you take 4.
yeah, in front. The only reason I put the 7 in front is so if I do something like this, it doesn't look confusing if the 7 is supposed to be under the root or not under the root. If I put it in front, it doesn't look as confusing. All right, and now last step, get rid of cosine with inverse cosine. Okay, so inverse cosine of -5 divided by 7 square roots of 35. I think I messed up my parenthesis. Like that. So that gives us an angle of 96.9 degrees. Any question on that? All right, so all those formulas we just did, that's what you'll be responsible to know how to do in 3D. So questions tonight, not very many. So it's 15, 17, 29 to 35 odd, 41, 43, and 51. Okay, so now, just a couple reminders. So there is no homework from the book tonight. Okay, we have the take-home test. And the test is going to open at 2:40. 2:40. And then it'll close, I think I said, like noon. And that's, what's that? That's 4:25. It's 4:26.
If you're like in the test and it hits 12, it'll kick you out.
Yep.
Oh.
Yep. It's going to just lock you out and submit whatever you have done. So open at 2:40 today, close at 12 tomorrow. If it's whatever you have done by noon, it's going to submit that. All right. So does anyone have any concerns about being able to get it done at home or use? You will need a graphing calculator, maybe for the inverse cosine when you're finding an angle. Actually, you could use a regular calculator. But if you set up the one on the Chromebook at the beginning of the year, you should be all set to use that for homework. Yep.
So no homework from the book, then what's the homework on top?
Oh, sorry, I didn't get to write down before I. Yeah, you don't have to do that.
Okay.
If you want to do that, I'll give you 6 extra points on the test.
Oh.
So yeah, I totally spaced out on the fact that the homework is the take home. So if you want to do that, that's 6 extra points. If you don't want to, you can just do the take home test. I would need that extra homework though. I would need it by tomorrow, the same day the time the test is due.
Oh, I'm not gonna be
Can I like email it my page to you?
Yeah, you could email it to me as long as it's by noon tomorrow.
Right.
Okay, so you will have 100 minutes.
Say that again? Number 17.
100 minutes.
So you have 100 minutes.
Already.
For a normal test, you have about 65 by the time we go over homework. So you have a little over an hour. This one you have pretty much a whole extra 40 minutes.
That's okay.
So you should, that's like having 3 periods, full 3 periods in school to take the test. That should be plenty of time. If you want to start it and come back to it later, you can, but make sure you do a save and exit, because if you open it and just leave it open on your screen, the time is just going to keep counting down. So if you want to come back to it, close it and come back to it. There also won't be a password on it either. Yes.
I'm in tomorrow. I'm in school with you in here, so I'm not have to worry about taking the test until tomorrow.
It's up to you. If you want to get it done so you don't have to worry about it, use whatever resources you have at home, you can. Or if you want to do it in class, you can, but then you won't have access to as many resources. Because if you're at home, you could use anything you have access to at home. but in school you might not have access to as much. So it's up to you. Is there anyone that has a concern about being able to get that done by noon tomorrow? Okay.